It's a pleasure and great honor, Susmita, to have you here at KIT. We know each other a long time, especially from the steering committee of ISVLSI conferences. You received your bachelor degree in electronics and electrical communication engineering from Indian Institute of Technology in Kharagpur, and the PhD degree in computer science and engineering from Yadvapur University, India, and faculty member in advanced computing, microelectronics in the Indian Statistical Institute, very prestigious institute in Kolkata since 1999. And presently, you are a professor over there, and during 93 to 99, you have been a reader in the Department of Computer Science of Yadavpur University, and then a postdoctoral fellow at Nebraska Lincoln. Really excellent career. We are really honored to have you as excellence fellow here at KIT. And I know you from your algorithm, logic, VLSI, physical synthesis and algorithm. You did a lot of conference and symposium and also magazine transaction editorships and organizations, and you have also here a lot of awards with receiving as president of the India Gold Medal summa cum laude at IIT Kharagpur in 1980, IBM Faculty Award in 2009, Distinguished Alumnus Award in 2020, and very important Woman in Technology Leadership from VLSI Society in 2022. So I don't want to waste more of your talking time, Susmita. The floor is yours, and we will see the challenges of designing quantum computing circuits. Please, the floor is yours.
Thank you very much, Dr. Roth, for the International Excellence Fellowship Grant, Ms. Pfeiffer, and of course, Professor Jürgen Becker, whom I've known for many years, as he mentioned. And when he visited Kolkata earlier this year to deliver a keynote address, and we met and we were discussing about research collaboration, and then it came up that how about visiting KIT, and I'm really happy that it happened through this program. So I would like today to share some of the works that we have done. The first part would be a little bit of introduction. I'm not sure whether all of you have had some exposure to what quantum computing is. There is a lot of talk about it. So let's see. Okay, that's the main building of Indian Statistical Institute, founded in 1931 by the visionary Professor Prasanta Chandra Mahalanobis. You may have heard about the Mahalanobis distance if you had a course in statistics, right? So he was a trained physicist who turned into a statistician later on, okay? And he feels statistics is a key technology which we see nowadays in whatever we do in engineering. So the agenda is a brief introduction, and then the main topics or main challenges of building quantum computers. Before we forget, I would like to list my collaborators in this area. Many of them were my former students or current, and this is a team from IBM Quantum Research with whom we have been collaborating. So, okay, what are the major drivers of quantum computing? First of all, you see in the picture over here, that's Charles Babbage's computer, and this is where we are now. But we are getting to very, very small transistors, which is almost at the atomic level. So one limitation is comes from theoretical computer science in terms of algorithmic limitations. So there are problems even today, which are known as the computationally expensive or NP-complete problems, as we know, which take a large amount of time to be solved on the traditional computers that we have today. We do have a lot of compute power with GPUs and whatnot, but still there are problems. As the input size grows, the running time could grow exponentially. Okay, so that was one limitation. And the other one is the hardware limitation. So you have in a chip of this size more than 1 billion transistors operating at gigahertz level. So you can imagine the amount of heat dissipation that happens. And even having 2 transistors very close by would lead to a lot of faults, etc., which would affect the performance of the system. So imagine TSMC is manufacturing 3 nanometer or 2 nanometer feature size of transistors. Just for your reference, these are what we know of in the physical world about the size or comparative size. So the red blood cell of humans is 7,000 nanometers. And we are going to have transistors of a few nanometers. So you can imagine how small these devices are. In fact, the ones in your pockets, I mean, all of us have at least one. In the mobile phones, you have ICs, which are not 2 nanometers, but it would be, the latest ones would be 45 nanometer or 28 nanometers. Okay. So these are kind of reaching the limits. So that's when quantum computing, quantum mechanics-based computing would be able to have some promise. Okay. So the promises are as follows, that, especially for optimization and simulation of large complex systems, quantum computing has promise of helping out. Okay, and the areas are diverse, starting from drug design, material design in pharmaceuticals and chemicals, and finance, then also climate modeling, which we know is still quite complex, even with your very good supercomputers, right? I mean, a week ago, if you check the weather, it says that it's going to be fine, it's going to be sunny, but the day before you find that it's going to be rainy. Okay, so climate modeling is very, very complex. And then, of course, other kinds of applications like, airplane or railway networks, autonomous vehicle design, and even, election prediction. Again, anywhere you have a very complex system with a lot of constraints, a lot of objective functions, combinatorial optimization, as you feel, and also in real life, the natural sciences, like in physics and chemistry, the simulation, it's analog, which makes it even more difficult. Okay. In astronomy, there's a huge amount of data, and again, how do we process that? Okay, a quick snapshot of the history. We know that in 1936, Alan Turing had first proposed the formal model of computation. In 1981, with this, we progressed with a lot of algorithms, etc., computational complexity, and so on and so forth. But we already knew by 1980s that there are some problems which are computationally difficult. You remember in 1971, Stephen Cook showed the first problem, the satisfiability problem, which is supposed to be NP-complete, which is, no polynomial time algorithm is known so far. So in 1981, Richard Feynman, the Nobel laureate physicist, had come to MIT. And I'll share an anecdote. I had joined as a graduate student there, and I had actually attended that lecture, just because I was a big fan of Richard Feynman. But what he said hardly, I mean, it needed a lot of physics. We studied quantum mechanics in high school, but all this thing of there's a lot of room at the bottom and you can use quantum mechanics to do computation, that didn't strike me then. Okay, it was almost 20 years later, while I was working with design automation of digital circuits, IC design and all. there was an issue of IEEE Spectrum, which talked about quantum computing, early 2000 something. And then I started wondering that how many of the algorithms that we are using in designing chips would be applicable to quantum logic circuits. And then I started reading up, and I found that there are similarities, but there are many extra challenges. In the meantime, after Feynman's talk, David Deutsch actually came up with the first quantum algorithm to show that quantum algorithms can be solve a problem exponentially faster than a classical computer. So he sort of established what is known as the quantum speed up. But then this problem, I'll discuss this, I'll just show you what it is in some sense kind of a artificial problem. I mean, even after he proposed that he's a theoretical physicist, people were not too excited. So what? I mean, where are we going to use this problem? Very soon, Peter Shor, he's an applied mathematician, he showed that this problem of given a very large integer, does it have factors? Or you want to find the factors of this large integer. If you want to do it with a classical computer, you would end up spending exponential amount of time, even today. What he showed that with quantum algorithms, you can do it in polynomial time. So that's an exponential speed up. Deutsch had also showed exponential speed up for a real life problem. And the reason this is a real life problem is public key cryptography based on RSA protocol, Rivest, Shamir, and Adelman, assumes that it is easy to multiply to large integers, which we have learned in primary school, but it is difficult to find factors with traditional algorithms. Okay? Even today, we don't have polynomial time algorithms to factor a large integer. Peter Shor showed that you could do it in polynomial time. So that made people sit up that, well, if we really build quantum computers, then all this public key crypto system on which e-commerce is developing in the late 90s or so, and later on in early 2000, that's going to be challenged, okay? So then people started looking at how can we build quantum computers. And the initial days, they started with NMR, that's nuclear magnetic resonance. But it took a long time for physicists, experimental physicists, to actually show experimental methods for measuring and manipulating individual quantum systems. So we have had, in a span of a decade, where quantum computing the technology has progressed, and therefore, at the same time, people like us have also seen what are the challenges with the technology. So a quick review of what are the difference of classical versus quantum. In a classical bit, the smallest unit of information that you have, if it's a two-state system, so you say that it's either in 0 or in 1, okay? And at any point of time, it can be in exactly one of the two states, but only one. Whereas in a quantum system, it's a continuum. So it can be in not only one of the two systems, but an infinite number of systems which are a superposition of this, a combination of this. That actually gives a lot of power, okay? Because if you have one bit, simultaneously you can operate on the two states at one go. Whereas in classical, you would have to do it separately for each value of the input, okay? If you have 2 bits, then in quantum, you have 2 to the 2, which is 4 possibilities. Okay, each bit can be either 0 or 1. So with 2 bits, you can have 4 possibilities. And on all four, you can do the operation of, let's say, evaluating a function. Okay, so as you increase the number of bits in classical, the power here increases linearly, but here it's exponential. So superposition is an important thing which is present in quantum domain and not in classical domain, and that gives power that leads to supports in some sense parallel operation in a massive way. Another very important feature is what is known as entanglement, and I'll explain it in a couple of slides down. Then there is another feature, which is the reversibility. And why is this important? Because as I said, that you have these very small transistors very close by, and whenever you switch something in nature, there is a change of energy. I mean, from sitting position to standing position, you need some energy, and you spend some energy, and whenever you spend some energy, you also dissipate heat. So if you have 1 billion of the transistors sitting very close by in nanometer range and changing states at gigahertz, which is 10 to the 9 per second, you imagine the amount of heat that's going to generate. And why is it important? Because as the temperature rises, the mobility of electrons which are the charge carriers of the transistors is going to go down, and your system is going to be slower. Okay, so you don't want to have that. So reversibility matters is related to power heat dissipation, and we'll see how. But on the flip side, in quantum computing, you cannot copy, and therefore you do not have any fan out. Okay, so that's where the logic synthesis, the digital logic synthesis techniques and testing, etc., you have to be different. And another point is that it's very fragile. It has very high error rates, and it needs cold temperatures so far. So it's better to have all the mundane tasks done by classical computer. We have a lot of computational power, but there are other kinds of tough problems, such as complex simulation and optimization, for which we will have these quantum processors. So you can imagine that you have a regular CPU, and for the hard tasks, some of the hard tasks, which the CPU is going to take a long time, you can ask the quantum processor to do that, give you back the result, and then you proceed with whatever you were doing. So the reversibility is an important concept. You say that a computation is reversible if it is bijective, in the sense it can go both forward in time and backward. That means from the output, you can uniquely determine what the input is, which is like a backward computation. Okay, so in some sense, it's information lossless. Okay, and that's the key to reversibility, because in 1961, Landauer had showed or derived that the minimum energy needed to erase one bit of information is proportional to the temperature at which the system is operating. So if information is lost, eraser loses information. Okay, so as long as you can have a computation where information is not lost, then you are not dissipating energy, and therefore the power dissipation problem for if you have reversible computation is going to, it's not that you have zero power, but you have very little power consumption. Okay, that's another reason why reversible computation had gained popularity. So the common, so as you can see, because it's bijective, the number of input bits should be equal to the output bits. And therefore, all the common digital logic operations that we know of, the 2-input AND, or 2-input OR NAND, we have one output. So that's actually irreversible. But we don't have to be so worried, because you can convert an irreversible Boolean function to a reversible function, but there's an overhead. You need some extra inputs and outputs to match the number of input and outputs. So imagine the OR gate over here. Here's a small example. This is irreversible because if you say a 1 at the output, you don't know exactly which of these three combinations were the inputs. So that's why you've lost information. But what you do is, to make it reversible, first of all, it's not 2 to 1. You make it 3:3. That means 3 input and 3 output. And so that means you have some extra input lines and extra output lines. So the extra output lines are called garbage, and the extra input lines, you can set them to constant values. And you see that this is the core OR operation, but by setting these, you can get a reversible OR gate. And if you notice that, this is the input size, so 3 inputs, that means 8 possible input vectors. And so if I write the decimal equivalent of them, if I want it to be reversible, it's a bijection, a 1-to-1. This is just a permutation of this. Okay, it's a 1-to-1. So for the same two distinct inputs, you do not have the same output. Each row has a different distinct output. Okay, so that's how you make. So home exercise, given a irreversible function, how many ways can you convert it to a reversible? So that's homework for you. Okay. Okay, so the NOT gate that we know of is of course reversible. By looking at the output, you know what the input. But the other two input, the AND or NAND, NOR, whatever you have, those are irreversible, but you can convert them. Now, a famous or a very common and powerful method of 2 input, 2 output is what is known as the control NOT. And we'll see a lot of this. What does it mean? That you have 2 bits. The first one is called the control bit, and the second one is the target. If the control bit is 0, nothing happens to the target. It just passes by. If the control bit is 1, then you have the NOT operation on the target bit. Okay, so you can write this in a matrix form, 2 input and 2 output. Okay, and as you see, if the x1, which is the control, if it is 1, then whatever was in the target qubit in the output line, you will have a swap over here. Okay, so that's the C0, and you can extend this to what is known as C²0. It's a 3 qubit. It's a Toffoli. It's known as Toffoli after the famous mathematician Tommaso Toffoli. And the reason this gate is important, here instead of 1 control, you have 2 controls. And if both the controls are 1, only then the NOT operation happens. But the reason this was important is because by setting the values of these controls in a certain way, you can realize this Toffoli gate as a NOT operation, or you can realize this Toffoli gate as an AND operation. So if you get AND or NOT, you have the universal gate set, right? So therefore, just a single gate can get universal. So far we are only in the zeros and ones domain, but I said you have a whole continuum. Yes, you're right. These are actually the reversible gates. Now here, so you can actually have any function here, and if you have a control line, you will have a universal controlled gate. Incidentally, this matrix representation that you have for these operations, they happen to be a special kind of matrix. They are called unitary matrices. If you recall your linear algebra course, a matrix multiplied by it can have complex entries. Okay, a matrix multiplied by the transpose of its complex conjugate, which is known as the adjoint. So the matrix and its adjoint, if you do the matrix multiplication, is going to give you the identity operation. That's the key to the reversibility. That means you can always find the inverse to do the backward computation. Okay, so that's why these are, the representation, reversibility, and unitary. So therefore, if you have a unitary function over here and add another qubit which is doing acting as a control, so you will have this, and this is used very often. Now let's look at something more complex. I said that, you know, you have a whole continuum. I showed you, in fact, let me just quickly go back to something which, so this is actually a unit sphere. It's known as the block sphere, which represents the state space. And you can have infinite number of states in here, which are corresponding to the quantum state over here. Fortunately, the state space has a finite number of what are known as basis states. So in this case, this is a binary system, so it has just two basis states, and any point on the surface of the sphere can be represented like this, and these two are called the amplitudes, and these can be complex values, but it has to also follow the fact that, you know, the magnitude of these two, if you take the square, should add up to 1. Why 1? Because this is how it's related to the probability of the you know, the system being in state 0. And so this is the probability of the system being in state 0, and this is the probability of the system being in state 1. You can have superposition of them, but the catch is that quantum systems are closed systems. If it is not closed, then the state keeps changing. So if you measure, that's an interaction with the environment, and therefore it collapses to one of the basis states. So that's the reason why you can't copy, because to copy you have to read, and to read you have to measure. The moment you measure it, in the original state gets disturbed. Okay, that's why you can't copy in quantum. Okay, so therefore no cloning, no fan out, and all that comes from this point. Okay, so let's look at some of the operations that you can do on a quantum state. So these are known as quantum gates, and this is on 1 qubit. For 1 qubit, we had a 2 by 2 matrix. For an n qubit, we'll have 2 to the n by 2 to the n matrix. Okay, the C0 was 2 qubits, so that's why we had 4 by 4. There are 4 possibilities of inputs and 4 possibilities of outputs. So this is the input possibility, and this is the output possibility. So this says that in that sphere, any vector to the surface of the unit sphere could be the state space. I mean the state. And on that state, if you a gate is an operation. If you apply Rx theta, that means you are rotating that vector about the x-axis by an angle theta. Similarly, Ry theta and Rz theta. And some more gates. So this is actually the NOT gate. If you apply, you know, a 0, you are getting a 1. And how do I get the output? So the way I do this is the state of it. Again, as I said, as a combination of A times 0 ket plus B times 1 ket, so the combination of the two basis states. Okay. So what you have is the state is represented, the 0 state is represented by a column vector 1, 0, and the 1 state is represented by a column vector 0 and 1. Okay, so then you apply this operation by multiplying the matrix with the state vector, column vector. So a matrix followed by a column, which you have to multiply, and the output of a matrix multiplying a column is again a column vector, which will give you the output state. So input state multiplied by the matrix for the gate gives you the output of the gate. That's how you can do the simulation of quantum systems. Okay. So this is actually the NOT gate, which is actually related to the rotation gates. And here are some more common gates. Okay, this gate is very important. This is known as the Hadamard gate. And the reason this is important is that you notice that if you place one column vector 1, 0, which corresponds to the 0 state, and multiply this, what you will get is 0 ket plus 1 ket divided by root 2, which means equal superposition of 0 and 1. Okay, so that is basically, so the north pole is 0 and the south pole is 1, and so the east side would be 0 plus 1 by root 2. And if you measure, the probability of the 0 state is half square of 1 by root 2. Probability that it will collapse to 1 state is also half. So that is why it is equal superposition. Okay, and that is for 1 qubit. Now, if you have n qubits, on each of them you perform Hadamard operation, you will get equal superposition of the 2 to the n possible states. Okay, and these are 2 qubit gates. Okay, so and then with this gate operation, what is a quantum circuit? Quantum circuit is basically a cascade of quantum gates, okay, and which are applied to qubits. Okay, so as I was saying that if you have this circuit here, so this is a 2 qubit C dot operation, this is a 1 qubit X, this is a 1 qubit Z, and this thing is a swap operation. Okay, and this is a qubit. So first on the 2 qubits you have C0 operation, then on the first qubit, the output of that, you apply X on the first qubit and Z on the second qubit, and then you do a swap operation. So this whole thing, the sequence of operations is actually in reverse, the C0 followed by, if you have 2 independent things, you use a tensor product to compose the multiple qubits and then swap. So in reverse order, if you do the matrix product and whatever is your input state vector is, you multiply that, you will get the output state vector. So for a circuit, how good is a circuit? That you measure in terms of how many qubits you are using, how many gate operations you are doing, and how not just the number, but also the number of stages. And one very, very important thing is, although this is a schematic for a quantum circuit, but unlike traditional circuits, digital electronic circuits or electrical circuits, the lines going from one gate to another, these are just schematic. There are no wires in a quantum computer. Okay? Those are just denoting time. That means at the first time instant, these 2 qubits have this operation. So if you look at a chip, you will be able to identify the gates, the transistors, provided you have a powerful enough microscope. Okay, and then the wires connecting the input, the output of a gate going to the input of another gate. Okay, in a quantum computer, there are no gates, there are no wires. Then how does it work? Okay, so what you have is actually the qubits, the closed quantum computing systems representing one binary system bit of information. Okay, and what is a gate operation? We are not seeing any gates. So how are the gates operating? So those are actually electromagnetic pulses which are applied on the closed system to change the state of the system. And how does a 2 qubit operation occur? You have 2 closed quantum systems in very close vicinity, where you apply enough electromagnetic pulse on both of them so that their state changes according to whatever you have defined the operation to be. Keep that in mind, okay? That's very important, and that's very different from what we have so far in digital logic. That's why logic synthesis for quantum computing gets needs different attention than so in traditional ICT technology, we measure cost, how good a design is in terms of the area it needs, the delay from the input to the output, how much power it consumes, and so on. But in quantum computing, and because it's reversible, we don't bother about power. We bother about delay, which is the number of sequence of operations, the length of the cascade. And there's no area because, I mean, it's only the number of qubits. So we have to reduce the number of qubits. And imagine qubits are expensive, very, very expensive. So for example, now we have superconducting conductor-based quantum computers. Imagine that you have to maintain them at very, very low temperatures. Okay, so even maintaining low temperatures, of course, needs power. So, but the computation doesn't need power. Now, so reversibility, we saw a property of quantum. I talked about superposition, and the last important property is the entanglement. So a state of two or more qubits, if it cannot be described as a product of its parts, then it is said to be an entangled state. So look at this circuit. I have two qubits, both in 0 state. Okay. After I apply the Hadamard, I get this. Excuse me, sorry. I get this superposition of both the 0 and the 1 ket. And the second bit remains 0. Okay, so this remains 0. Because they are a composite system, you do what is known as a tensor product. And over here, what you get is this. Okay, these two states, 2 qubit states. And then after you perform the C0 operation, now remember the C0 operation, this is for the first qubit. If it is 0, then nothing happens to the second qubit, so this remains unchanged. But here the first qubit is 1, so this flips to 1, 1. Okay, so over here, this is what you find, and this is what is known as an entangled state. And why is entanglement useful and unique? Because that is very much required for what is known as teleportation, which means that suppose you bring 2 qubits or 2 individual quantum systems very close by, and by this kind of operation, you put them in an entangled state. Then if you physically transport both the qubits very far apart, because they are entangled, if you perform an operation on one of the qubits, even though they are physically apart, the other qubit also is correlated, and you can have information of what this happened to this qubit. So that is useful in quantum cryptography, which I'm not going to talk about today. But it's another very powerful area of research which is coming up. So with all this in quantum computing, we saw that not only in cryptography, the Deutsch's oracle problem, and all this. So those of you who are interested, I would request you to visit this website, which has the list of quantum algorithms discovered so far and how much better they are compared to classical computers. I think I'll speed up. I'll just discuss the Deutsch-Joshua problem. So the input is a Boolean function with n bits input and a single bit output. It's a non-reversible. You can convert it to a reversible one. And you are told that it is, you don't know what the function is, but you're just told that the function is either constant, that for all possible inputs, it gives the same output value, or it's balanced. That means for half of the possible inputs, so if it's an n qubit, you have 2 to the n possible input values. For half of them, it is 0, and for the other half, it is 1. You don't know which half, I mean, which ones. So your job is to determine whether the function is constant or balanced. This is the problem which Deutsch studied for 2 inputs, and then with Joshua, he extended it to n inputs. So for 2 inputs, what happens? in the classical sense, you would have to evaluate for, if you have one input and one output, then the input could be either 0 or 1. There are two possible inputs. Okay. In classical, what you will have to do is you'll have to evaluate f of 0 and then f of 1. That means two evaluations. He showed that in quantum, you can do it in one evaluation. So just, half the time. Who cares? Deutsch showed with Joshua showed that if you extended it to n bit, that means 2 to the n possible inputs and one output, then you can do it in one step. That's where the exponential speed up was shown. Okay, and essentially, I won't explain all of this. These are so this is the function. This is the block related to the function. Essentially, when you measure over here, if the function was constant, the output will always be in the 0 state. That's how he set it up. And if it is a balanced, then this will never be 0. Okay, that's how this was designed. And by looking at this output only with a constant number of operations, 3 operations, they could solve this. So actually, if you see the speed up, if you do classical query complexity, you would need to evaluate the function at least this many times, right? We are told half of them are zeros and half of them are ones. So for the first half, if you get all zeros, then you check one more. If it is a 0, you know it's constant because you're told that it's on either constant or balanced, but nothing in between. So with only these many, you can you need as many as this for classical query. For random, you can do better, but with quantum, you need only one evaluation of the function. Okay, so the traditional classical polynomial time and the exact quantum polynomial time, this is a problem which actually separates them, because this problem is not in P, but it's in exact quantum polynomial time. Okay, so the next problem is the Shor's algorithm. I won't go into the detail, but this just fascinates me, the idea. Okay, I'll just tell you. So this is actually one very big, long integer, okay, written like this. And this is actually the product of these two very big integers. Given this, how do I find the factors? That was the problem he wanted to solve. The best classical algorithm takes exponential time. So if you have a 300 digit, it's going to take these many years. 1000 digit is going to take these many years. But with Shor's algorithm, just a few hours is going to solve. The key idea is actually very neat. It's something we studied in almost primary school, maybe early secondary school. Imagine I want to factor the number 21. Okay, choose another integer less than the number I want to factor, and it should be relatively prime. That means no common factors. So if this is a famous result, a number theoretic result, if you raise this number to powers and compute modulo, so 2 to the 1 modulo 21 up to 2 to the 4, the values are less than 21. So whatever is the value, that is what you get. When you get to 2 to the 5, it's 32. So 32 modulo 21 is 11. Remember, modulo, that's the remainder. And when you go to 6, it's 1 again. So I had 1 for 1, 2, 8, 16, 11, and then 1 again. So it was actually proven that this is a periodic function. And this number 6 here is what is known as the periodicity of that function. So that means, now the beauty is that if I take the greatest common divisor of 1 minus whatever, so then if I compute this value, I find the periodicity and I compute this value, which is 8. So 1 minus that times this, and 1 plus that times this. If I take the greatest common divisor, these happen to be the factors of the original number. So this is what we said, right? What is r? X to the power r modulo n is 1. That is what gives the periodicity. And what was y? Y was x to the r by 2 modulo n. So let's call that y, okay? So that means y square modulo n is 1. Does everybody agree with me? X to the r modulo n was 1. And y is x to the r by 2 modulo n. So if I take the square of that, then I get x to the r. Okay? And what is y square modulo n 1? That means y square minus 1 is divisible by n. Right? So that means, and what is y square minus 1? That is y plus 1 times y minus 1. Modulo n is 0. That means modulo n 0 means no remainder. That means there must be, I am dividing this product by n, which has some factors. That means some of the factors are going to cancel out. Exactly. That means n is going to divide this exactly. Okay. So the factors are going to cancel out, and this value is in this range, which means that y minus 1 and y plus 1 are less than n minus 1. And therefore, if I take the GCD of these two, these will be the non-trivial factors of n. This is actually grade school mathematics. So why didn't people use this for factorization? What's the catch? The catch is finding that r. In classical, you would have to go through all of them till you found the one. What Shor showed that you don't need to do these exponential number of steps. There is a quantum algorithm which can give you this value r in polynomial time. Once you have r, the rest is classical. You know, finding GCD is polynomial time. Okay? So finding that r was the stumbling block. Okay? Okay. I'm going slow. So what do we need to build quantum computers? We need theoretical computer scientists who's going to design the algorithms. We need physicists who's going to have both experimental and theoreticians. And our business is over here to build quantum computers. And to build them, we want them to be scalable. We have to be able to initialize and have reliable gate operations. The important thing is the fragility. That means this, I said, closed quantum system. Okay? So that means if the state changes, till the state changes, I have to do the computation. And that is what is known as the decoherence time. And that's not very high. I mean, for superconductors, it's of the order of microseconds. For quantum dots, it's milliseconds and so on. So within milliseconds, you have to do the entire computation that you want to do. And the measurement also should be reliable. Since there's no cloning, how do I test whether it's doing the right thing? And control is classical, that the electromagnetic pulse that I have to apply for the gate operation, that is classical. So that also has to be very precise. Okay, so it's quite complex. And just as we have the VLSI design flow, we can talk of quantum circuit synthesis flow, where you start with the quantum algorithm, and in the quantum algorithm, some part is classical and some part is quantum. So the classical function, all of that has to be reversible. So the classical you convert to reversible, the quantum of course is reversible. And that's at the behavioral level. Then you get the logic, and maybe it's not fault tolerant. So you have, depending on the particular technology, you have to map them to available gates from the gate library and then make it fault tolerant. So here you have the fault tolerant quantum logic. And then, of course, further on, you need error correcting code, which you will need to take into account to actually map it on the device that you have. Okay, so these are the steps in VLSI design. You also have behavioral description, structural, gate level, physical. Similarly over here. So our research, we did come up with something here. This is available, the FTQLS system, and also physical design aware quantum circuit systems synthesis. For the technology mapping, we do that for, so the problem is that till now, these 6 technologies are being pursued. Actually, superconducting, quantum dot, and ion trap are more, and the photonics ones are more promising. The catch is, of course, that's there in CMOS also. We talked about quantum gates, different kinds of quantum gates, but not all quantum gates can be are primitive gates in a particular technology. So for example, in superconducting technology, only the rotation gates can be obtained for 1 qubit operation, and only the CZ gate can be obtained for 2 qubit operation. Okay, so as a result, depending the logic synthesis you can do in terms of available different kinds of gates, but when you are actually transferring it to a particular technology, that's what's known as technology mapping, you will have to make use of what are known as logic identities. That means if, say for example, in oops, what happened? Yeah, so in superconducting, for 1 qubit, we don't have the Hadamard. How are we going to do superposition? Okay, so what we can do is an Hadamard operation is equivalent to an Rx followed by Rz followed by Rx followed by another Rz. Okay, or maybe an Rz and Ry. These are phase gates. Okay, similarly for C naught, which are not available in these 4 technologies, you can express them in terms of equivalent whatever primitive gates you have. As a result of this, what happens, the cost tables, you have to come up with cost tables, right? The number of operations, what are the operations and what is the technology, with that it will vary. And similarly, the number of time cycles, okay? So when you are doing logic synthesis, you have to keep these in mind when you are optimizing the number of qubits, number of gate operations, and number of cycles. So that's what FT synthesis, fault tolerant synthesis, did. We published, this is quite old work, but it was a very landmark work. And the optimization is done in actually in 3 stages. First, in the behavioral domain, where you don't know what technology you're going to use. Then you make use of the particular technology. And finally, you convert it to fault-tolerant gate set. Although you have some primitive gates over here, not all of them are fault-tolerant. So again, you will have to make some more conversion over here. So 3 levels of optimization to get something which is doing well. So here is an example. So for a 4 qubit circuit to do quantum Fourier transform with 4 qubits, if we just were in the non-fault tolerant domain, that is, do the first 2 levels of optimization depending on the kind of technology, this is the kind of reduction you get in number of operations and number of cycles. Okay, for a larger circuit, you get almost about the same or slightly better. But if you also do it in the fault tolerant domain, that is 3 levels, the improvement is quite better. Okay, so you can see that, you know, this is the improvement you get over here. Okay, and depending on the technology, this varies. Okay, then the physical circuit, so that was at the logic level. Okay, this is no physical. So what happens is this is the actual physical qubit. Okay, and to be able to do error correction, which I'll talk about a little bit if I have time, a single logical qubit is actually, it needs multiple physical qubits to be able to do error correction. Okay, so as a result, and there is a famous result that if you do this recursively, then your error correcting capability increases, the probability of error decreases, okay? But imagine the number of qubits is increasing, and qubits are very expensive. Not only that, where do I map the specific qubits? That is known as the placement problem. And say, for example, over here, I have a circuit which has 9 qubits, and they are arranged in a 2D array like this. And I need to do an operation which involves S1 and S8, but they are not close by. I have to bring them close by to do a C0 operation, okay? So the way I can do it is first a swap between these two. So then I bring S8 over here, then another swap between these two. Only then S1 and S8 are close by, and then I perform whatever operation I wanted to do. So this is called a swap chain, and I want to minimize the number of swap operations. If the initial placement of the qubits is such, then the number of swap chains can be, the length of the swap chain is going to be smaller. So let me show you an example. So suppose this is a digital logic, a quantum logic circuit. These are C0 gates, okay, 2 qubit gates. But to have the C0 operation, the Q0 and Q5 physically, the S0 and S5 should be next to each other, okay? So in order to do that, I do some swap operations before I can do the swap actual C0 operation. After that, the next C0, for the next C0, I need one more swap. And so on. The whole, although I had 6 operations, I need 6 more swap operations to be actually able to do the operation correctly, okay? And that's because I had mapped these qubits in this manner: S0, S1, S2, S3, S4, S5. This was the placement that I used. But had I used this placement, S0, S1, S3, S2, S4, S5, then the single swap operation would be enough, okay? So the placement problem is, given this circuit, what is the mapping of these qubits on the 2D grid, okay? And if I can do it well, that overall cost of the circuit will be reduced, okay? We produced what is known as the physical aware quantum computing synthesis. So if you want to have a circuit with Q qubits being placed on an R cross R grid, we could do the placement in this, the algorithm was a greedy heuristic. We could do it in this way, and the routing was slightly more expensive. So that is something which could tackle a fairly large circuit, okay? Now, let's look at where we are. Last year, there's a computing community consortium. They published a report on quantum computing, the progress over the last 5 years. You see the number of gates is still over, around 10 to the power 3 or so. This is the quantum computing as in 2023. Quantum control over here, and you need to have scale-up hardware, error correction, and so on. So with a limited number of qubits, you can perform very little as far as we are concerned. This is the development roadmap published in 2024 by IBM. The initial hardware which was available to over cloud was a 27 qubit. Now they have stopped it, and they allow this 133 qubit one, or the 127 qubit. Basically, you can pay for 127 qubit hardware and map your quantum algorithms and see how they run. Although they have produced Condor, which is 121, and some reports of Kookaburra is coming, but they are not open to public because the error rates are still very high. Okay, so still technologists are working on that. So we said we would do error correction to make reliable, but to do error correction, you need more qubits. So then you are left with very few qubits to do the actual computation. So actually, Although we talk about quantum supremacy, in reality, we are still not in the fault-tolerant error. What we are in, what is known as NISQ error, noisy intermediate scale quantum error. Okay, so let me just tell you about quantum error correction, just 2 slides, why we need it, and then we'll go to the so in Boolean, it's clear that you have. But in quantum computing, you may have something like this. What does it read? What does it say over here? Is it true or is it false? It could be both. Okay, so imagine that you have a 2-qubit entangled state. Remember the one we had over here? This was the state we created. This is the circuit we had. Okay, so the H looks like this and so on. And if you run on a simulator, because it's like this, it will collapse to either the 0-1 state or the 1-0 state. These are the probabilities. Okay, this is on a simulator. But if you run on a machine, this is what you will get. Okay, this is just probability. And I must tell you something. Quantum computing is probabilistic, as I said. The algorithm that you design, the whole purpose is you start from the input state and you keep applying operators in such a way that it changes to a state in the state space which has the highest probability, and it corresponds to the correct output value. So therefore, when you measure, you would measure that state, and if you measure that, the very high probability that you will measure that state, and therefore you know the output. But it is probabilistic. There is a non-zero probability that you will the outcome of the measurement might be a state which is not corresponding to the correct output. So that's why, as in probabilistic computing, you will have to, if you do program your quantum algorithm using Qiskit on a IBM hardware, you will have to run it for a number of trials and take the average of it. And because it's probabilistic, the idea is with a very high probability, you will get the correct output state in most of the trials. Okay, so that's why, because there is a non-zero probability of getting the wrong states, so these are because of erroneous operation on the quantum state. How can we do error correction? Well, we can get stronger by encoding, which means, as I said, for a logical qubit, you have a number of more than one physical qubit. Okay, so there are various error models like bit flip, phase flip, and the good thing is that any quantum error correcting code that can correct for these kinds of errors, so this is the bit flip error, this is the phase flip, and this is the combination of both, can correct any error on a single qubit. So the same Shor who proposed a meaningful factoring quantum algorithm, he went on to also propose a quantum error correcting code. And you can see that one logical qubit needs 9 physical qubits for quantum error correcting. So to do error correction, you need a lot more resource. And very soon 2 others came up with slightly better. And it was also shown that you can't do any less than 4. Actually, 5 is what. So when we do synthesis, it has to be aware of the kind of error correction that you are doing. And we did some work in this area. And particularly the placement algorithm that I showed takes care of the various, all these error corrections. The drawback, so how do I design this? As in classical error correction, you use repetition to correct a bit error. Okay, so instead of a 0, I use 000. So if there is a mistake or there is a single qubit error, only one of them is going to be erroneous, and we know that this is closer to, so if I get 010, I know it's closer to 000 than to 111. So it must have been a 000. That's how classical error correcting code works. Similar idea of quantum, but you can't copy. So what you do is you use this method to encode, and and here in classical you read the so you transmit. To transmit a single zero, you transmit 3 zeros. You read that, and if you get 0 1 0, you know it's 0 0 0. Here you can't read. If you measure, then the state is disturbed. So in order to measure, what you do is you use some ancilla qubits, and you kind of design such a circuit that you can measure the ancilla qubits, and looking at the value of this, you can figure out which of these three the error occurred. So for example, if the syndrome is 1 1, okay, that means, so the first qubit here checks whether these two are same, and the second qubit here checks whether these two are same. Okay, so if both are 1 1, that means the common one is the second one, and that is the one which is wrong. Okay, that's how it works. So that was for the bit flip, and similarly for the phase flip, you do things like that. And the circuit required for error correction on a single logical qubit is as big as this for error correction. So error correction is very expensive. Okay, and not only that, look at this. This is a CNOR operation. We would need these two qubits to be next to each other. So to do that, we will need some more swap operations. In the meantime, some mathematicians proposed in the early 2000s, not nearest neighbor, unlike this kind of code, a different kind of code, which is 2D topological, which is, only the nearest neighbors are on a square lattice. You have the physical qubits, and therefore only they are used for doing the correction. But there, one logical qubit, here Bacon-Shore needed 9 physical qubits. For the surface code, one logical qubit could need 9 or more. Okay, actually 17 in some cases. So let's look at the other option that we have now, noisy intermediate scale quantum error. These are noisy, so don't think about error correction. Only a few hundred qubits and a shallow circuit, because otherwise errors are going to build up. And what we have now is what is known as hybrid quantum classical algorithms. So this is a quantum circuit. I want to do you can use them for a whole lot of applications. Let me focus on combinatorial optimization. What is done is you have a classical optimizer, and you set up the particular optimization problem corresponding to that. You set up the quantum circuit like this, which is parameterized. These theta i's are parameters. So you have one iteration of the classical optimizer, which sort of gives the initial values of the parameters with which you run the quantum circuit. You measure, look at the output, and there is a target output. By that, you can estimate the cost. If the cost is high, that means with that you update the parameters and you iterate again till you have a very good cost. So a quick example, suppose let's look at this problem, the max cut problem, which is an NP complete problem. The input is a graph. You have vertices and edges. I want to a cut is a set of edges which, when removed, will make the graph disconnected. Okay, I want to find a cut which has the maximum number of edges. We also have the min cut problem. Min cut we can solve in polynomial time. Max cut for a general graph is NP complete. So to do this, we can use this kind of a circuit. For each edge, you have this sort of a circuit over here, and once the operation that you do to solve this is, once you evaluate this and another time you evaluate this. So basically, alternately, These you need a lot of parameters which are to be fed into the sequence of operations that you do, and you keep repeating them. After that, the expectation value is corresponding to the measurement. Look at the feed it to the optimizer, get a new set of values, and you run this. Okay. So the good thing is this was proposed by a scientist in MIT, Ed Parry, and he showed that this is known as a QAOA, quantum approximate optimization algorithm. So you can, with a classical approximation algorithm for max cut, you can go up to 0.83 times the maximum, which is the approximation factor. With this, you have to iterate and you can get close enough. But the problem is that, first of all, if this is the circuit that you have to use, the error probability of the 2-qubit gates in the max cut, we needed some C0s and some rotation gate. The 2-qubit gates are very error prone. Okay, so therefore, what we want to do is to reduce the number of 2-qubit gates, and we have used some graph algorithmic approaches to do that. First of all, quantum computing wise, when can we remove? So for each edge, we have this circuit, and if you remove the first qubit, then we get equivalent. But the catch is that both this elimination is valid only if you had a equal superposition over here. Okay, so this works only for the first iteration of the QAOA. So suppose you're given this graph for max cut. These are the vertices. Okay, if you do depth first search, okay, so that means 0 to 3 is the first edge, then from 3 to 4, 4 to 2, and then 2 to 5, and 5 to 1. That's the order in which I traverse. And here, so Q0 to Q3, that is the edge, that is the C0 corresponding to this edge. I mean, these two C0s, I can remove this one. Then 3 to 4, these two C0s of them, I can remove this one. Then 4 to 2 is this one, I can remove this one, and so on. So in a graph with n vertices, the depth first tree is going to have n-1 edges, and so you can remove n-1 C0s. That's the maximum that you can. But the catch is that the trouble is that you can't perform, let's say, this Q0, Q3, and Q4, Q2. These are separate qubits. So I could have done this operation in parallel, but now I can't do this. Okay. So although I reduce a lot of C0s, but the depth of the circuit is more. So again, we had another, it's the height of the spanning tree. This is a longer one. So this is, you have depth 14. If you have a shorter depth for spanning tree, you have shorter depth, but that's not all. These two have the same depth, but this has, smaller value, whereas this is like this. So they have different depths. Okay, this has depth 3, this is depth 2, but still they have the same circuit depth. That means number of cycles. So you have to do some kind of a heuristic cost function where I want to have the branching closer to the road, because edges associated with a common vertex, you have a common qubit, so you can't remove both the C0s. Okay, so with this, I'll skip this, I'm running out of time. What we found is the traditional QAOA was like this. With that first, we got some reduction in, so this is the probability of error. And with our method, we could get much better, not only reduction in circuit, but the error probability also was very low. And you scale up to more vertices, and depending on the branching that you allow, you can actually have different depths of circuits. And but that was irrespective of the hardware map. Okay, not all were connected. Okay, so if I take that into account, then of course I get different number of swap gates. Okay. So I have to modify the cost function. Our first heuristic algorithm would need 6 swaps, whereas if I modify the cost function, and then I get 3 swaps. And on random graphs, I mean, random graphs means that the probability of having an edge, you can vary, you can actually reduce quite a bit. Okay. Not only do you need to reduce at the logic level, but when you are mapping onto the actual available hardware, see, as I said, like the placement problem, these were the 5 qubits and this is where you had connected. But because I'm doing this C0 operation, I need to do 3 swaps to bring them close by and then back again. So I have to do the placement, but we did this work in 2015, the PAQ-CS, but now with the technology evolving, we find not only are they all connected, I mean, all the connections are there, but also the qubits have different error rates. Okay, not all qubits have same error probabilities. Not all gate operations have the same error probability. So when you do the placement, you have to take that into account. This is an algorithm which tries to use subgraph isomorphism. So this is the target. What should I say? The target device that you have. This is the circuit which you have to map it over here. And what you do is in the entire thing, you move around and find where are the good qubits and give a score. And then suppose I have these many available hardwares and these many circuits. I want to do a job scheduling. I have to, and this, if I place all of them in the best hardware, of course, I will get best fidelity, but the execution time is going to be more. But with the noise profile, if I do them all in parallel, then it's going to be worse. So what we did was we took the fidelity, noise profile, and the quality, and yet if you want to achieve a certain target deadline, we had a ILP solution and also a greedy algorithm, which gave quite a bit of good fidelity as opposed to without anything. But if the number of hardware is more than the available circuits, you can do a simple, min cost maximum matching in a bipartite graph, and you get twice to thrice better utilization of the hardware. We also did some work on the same hardware. You may not be needing all the qubits for a particular circuit. So on the same hardware, I want to map more than one circuit. So that's, again, a scheduling problem. I don't want 2 qubits from 2 different circuits to be very close by. So there's a buffer between. So I have this map, the coupling map, given coupling map. I have a number of circuits. I have to map them. I have a number of placements, and I know the scores of the placement. So this is a multi-objective optimization. How do I make the best use of the available qubits without much degradation of fidelity, and also get good execution time? Okay, so these are some problems which we computer scientists and engineers would be interested in, and I have gone far beyond my time. Let me stop here and talk about what we need to do still. We need quantum algorithms, exact and approximate, to solve real-life applications. In the synthesis domain, even in the NISQ domain, we need space efficiency. The Shor's quantum error correcting, the Shor's factoring algorithm that I mentioned, that needed, if you had n qubits, okay, that would need n qubits, and the number of gate operation was order n square log n, okay. That's quite a bit, number of gate operations. Last year, Regev and his student improved that from n square log n to n to the 1.5 time log n, but the number of qubits increased. And recently, another improvement has happened, having the same space complexity, that is the number of gates and number of qubits, but that probabilistic computing was more robust in the sense of both space efficient and robust. That means you, let's say you have to do K number of trials before you can say that, given the error rate, you have to do K number of trials before you can trust your output. Okay. Even if a certain percentage of those K number of trials are erroneous, can your circuit still give you correct output? That's what they showed very recently, a couple of months ago. So these kinds of works need to be done. And of course, now people are having 3D grids of qubits. I showed you planar coupling maps. So with 3D grid, how can you do physical mapping? And of course, with noisy quantum resources, depending on the technology, how can I optimize more with the noise profile? Getting the noise profiles is a real challenge because you have to do thousands of simulation. I haven't touched upon testing quantum circuits, verification of quantum circuits, and also the security aspect. Some research has just begun, okay, but these are challenging. We did some work on multi-valued quantum logic circuits because with multi-value, say for the same number, in transistors and CMOS technology also, actually it's analog, right? We have imposed digital binary in the sense there's a threshold, any voltage above the threshold is 1 and below it is 0. In quantum systems also, depending on the energy levels, you can have a whole infinite number of energy levels. We are just using the ground state and the first level. We can use one more state. And why? Because with K qubits, you can represent 2 to the K states. But with K Q trits, that means you can have 3 possible states, you can represent 3 to the K. And you can have qubits. But control is difficult. Design, we did some work, and we also proposed, there was a general quantum error correcting code for, Gottesman had given it for qubits, but that did not pay attention to the implementation, the circuit part of it. So we proposed another QECC for qtrits. And actually, I had visited MIT, and just one discussion with Peter Shor showed us that how we could do this for qtrits also. And we got a quantum logic circuit, which is much smaller and much more efficient to do the quantum error correction, okay, for multi-valued. A lot more needs to be done. Some logic synthesis techniques are there. There have been some implementation of photonics-based 3-state system. We need more QECC, more efficient circuits. Error syndrome decoding. Remember I said that in the Shor error correction, you had 2 ancilla qubits. And if you got 1, 1, you knew that the second qubit. If you got 1, 0, you would know it was the third. And if it was 0, 1, then it was the first qubit. You know exactly which qubit was erroneous. And knowing that, you can do the correction. Okay. But what happens is if the number of qubits increase, then decoding the syndrome, that means there could be more than one error which will give you the same syndrome. So then decoding the error itself is an NP-complete problem. There have been some graph theoretic algorithms to do that, but we showed that there can be cases when they actually decode it wrongly, and if you decode the error on a wrong bit and you change that, you actually increase the error. The original error was on, let's say, QI, and because of the decoding, it says that QJ is erroneous. You go and flip that. So now you have both QI and QJ, both erroneous. So so what we did was we used some machine learning approaches. There were some previous researchers who did this, and we also did this for surface codes and some very recent codes and got quite impressive results. So this is another area where work needs to be done. And finally, people have been, quantum computing on one side and AI on one side. What's the relation between this? Quantum machine learning is coming up, but there are skeptics who say that, Why can't I do all this complex computation with AI on a supercomputer with a GPU? You need lots and lots of data. So whether quantum computing can handle so much data, because you have to prepare the initial states, you have to do measurements, you have to do multiple trials. So, but quantum computing is good at complex simulation where the input and output space is small, but data is small, but internally you have to do a lot of processing. That's what quantum computing is good for. In AI, you have large volumes of training data which you have to handle. So maybe what we will have in the future, as I see, is quantum processor-aided supercomputing, where you may use AI. So that's where we are heading to, and IBM, Google, Microsoft, they are also now sort of trying to get there. Okay, I stopped, and thanks a lot for your patience and your attention.